And another example of problems that you might come across are motion problems. Motion problems are typically a distance equals a rate times time problem, where d equals distance, r equals rate, and t equals time. So let's imagine a situation where we have two planes. One plane that flies into the wind and another plane that flies away from the wind. What we know in this situation is that it takes the plane only 3 hours to fly 450 miles with the wind. But going into the wind, it takes 5 hours to travel that same distance. So we want to find out, well, what is the rate of the planes? How fast are planes traveling in this situation? So to begin to build an equation or build a system here, we need to start to piece together some information we have. And it begins with distance equals rate times time. Let's develop some unknowns. What are some things we don't know? Well, one is we don't know the rate of the plane in still air. How fast does the plane normally go without the wind? So we just kind of label that like x equals the plane. And then the speed of the wind we don't know, so we're going to label that. So how would you describe then the plane that's traveling with the wind? Well, that rate then would be the rate of the plane plus the rate of the wind. And it can do it in 3 hours. The plane going against the wind, well, again, or against means the rate of the plane minus the force of the wind, and it takes it 5 hours. And the distance on both of these is 450. So now we have a system. And on the system, notice that both of the rates equal 450, so I can set both of the rate times times equal to each other. So one could be 3 times x plus y equals 5 times x minus y. Because both of these equal 450, so I can set their values equal to each other. Now we can solve it. I need another equation in there. The other equation I need is actually, I think I may have jumped ahead of myself here now that I think about it. This might be my system right there. I just said equal to begin with because I just got carried away with the wind. So let's back up a step then, and let's just work that out. So one equation is 450 equals 3x plus 3y. And the other one is 450 equals 5x minus 5y. All right, I can live with that. 2 equations, 2 unknowns. Now let's scale them both so we can get a variable to drop out. So let's multiply the top by a 5 and the bottom by a 3. So in doing that, 4 times 450, or 5 times 450, 450, 900, 1800, 2250 equals 15x plus 15y. Scale the bottom one by 3, 900, 1350. $15x minus 15y. The y's cancel out. So if you add them together, I have 36 equals 30x. Solve for x, divide both sides by 30. And 3 goes in that, 12, 120 is what my x is. So the speed of the plane then in still air, which is what my variable was, is 120 miles per hour. And then if we wanted to go through, we can figure out the speed of the wind by back substituting that in to one of those equations up there and figure out what the speed of the wind in that particular case. But I was interested in the speed of the plane in its normal day. Well, maybe I am a little curious about how fast it would be going. So 120 plus wind is, I got to find the right equation. Right here is where I want to do that at. That's 360. 90 equals 3y. Y equals 30. So it looks like the speed of the wind is 30 miles an hour. Speed of the plane is 120 miles an hour, given the information that we had to begin this problem, which is a motion problem that we can solve through understanding how to solve a system. And maybe there's one more piece of information. I guess we can kind of look at that. If we know the speed of the plane in still air was 120, how fast was it going into the wind? Well, that'd be 120 minus the wind, which was 90. So it was going 90 miles per hour into the wind. And then with the wind, it was 120 plus the 30, which would make it 150 miles per hour. With the wind, it was how fast the plane was going. And then obviously in still air, it would be going 120 miles per hour.